Cool. Boom. Cool. Welcome back, everybody. I hope you all had a great spring break. Let's go ahead and recap what we talked about before the break. So it's been a little while, so I want to go ahead and just quickly discuss the concepts that we talked about in the last week before the break. So before we took off for spring break, we started getting more into the theory of linear algebra. We talked about the range and null space of a linear transformation. So who can tell me what the range of a linear transformation is, just intuitively? What's the range of a linear transformation A? So let's say we have our domain and our codomain, right? So what would the range of a linear transformation be? It's the set of vectors in our codomain that can be reached. It's the set of vectors in our codomain that can be reached by what? Right. So if we have a linear transformation A, so remember when we're talking about these subspaces, it's always in reference to some linear transformation A. So the range is the set of points that can be reached by applying A to any vector in our domain. Right. So this here, this would be the range of A. It's the set of points that can be reached by applying our linear transformation to vectors from our domain. And what was the null space? What was the null space of our linear transformation? What was that all about? Okay, so it's the set of vectors in which space? In the domain. It's the set of vectors in the domain that get mapped to the zero vector when we apply A to them, right? Okay, so this is an important concept. The range and null space of a linear transformation is very, very fundamental to linear algebra problems. And as we'll see, it's fundamental to control problems and observer design problems going forward. But these are the two subspaces associated with our linear transformation A. We also talked about the rank and nullity. Who wants to tell me really quickly what the rank and nullity represent? What is the rank of our linear transformation? Sorry? It's the dimension of? Right. So it's the number of, so probably the best way to think about the rank is it's the dimension of the range of A. The rank is the dimension of the range of A. The nullity is the dimension of the null space of A. Okay, and we talked about how the rank and nullity of a linear transformation relate to the number of linearly independent rows and columns. And there's an important theorem that I mentioned as well, the rank nullity theorem. Who can tell me what the rank nullity theorem tells us? It's an extremely important theorem. What does the rank nullity theorem tell us? The dimension of the domain is equal to the rank plus the nullity. Exactly. So that's an important thing to remember. If you know the rank of a matrix, you can also know its nullity through the rank nullity theorem. We also talked about the four fundamental subspaces, which I've alluded to here. These are the four subspaces associated with linear transformation. We have the range of A, the null space of A, the null space of A transpose, and the range of A transpose. And we showed that any vector in our domain can be represented as a linear combination of a vector from the range of A transpose and the null space of A. And similarly, any vector in our codomain can be represented linear combination of a vector from the range of A and the null space of A transpose. And this is going to be important going forward today. We also talked about one-to-one and onto transformations. One-to-one being that the transformation, every vector maps to a unique element in the codomain. So every vector in the domain maps to a unique element in the codomain. And onto meaning that every vector in the codomain can be reached through our transformation A. All right, so these are important concepts. Today, we're going to take these concepts and we're going to extend them a little bit. We're going to look at an extremely important and extremely general problem that you will encounter in engineering at some point if you haven't already. We're going to be looking at equations of the form AX is equal to Y. So this is kind of the fundamental linear system of equations. And we're going to be looking at overdetermined and underdetermined problems and how these different problems relate to the four fundamental subspaces that we talked about last week. And at the very end, we're also going to talk about how these different problems relate to control and estimation. And as you'll see, we'll talk about how specifically control relates to the underdetermined problem, whereas observation or estimation relates to the overdetermined problem. Okay, are there any questions on anything we covered last week before we move on? Any questions about the four fundamental subspaces or related concepts? Cool. Well, let's go ahead and get started. Before I can talk about overdetermined and underdetermined problems, I have to do a quick review of matrix calculus. So some of you may have seen this, but we want to talk about the gradient of a scalar function. Okay, so let's talk about the gradient. Who remembers what the gradient of a scalar function is? Has anyone encountered this in any of your other classes? Okay, the gradient of a scalar function, which we will call f, that takes us from Rn to R, the real numbers. So it maps us to a scalar. It takes us from our domain of vectors and it maps us to a scalar. The gradient of a scalar function with respect to a vector x in Rn is given by the following expression. This is a review of matrix calculus. You may have learned this in Calc 3. So if we have a scalar function df by dx, what we do is we take our scalar function and we compute its partial derivative with respect to each element of x. So we would have df by dx1, df by dx2, all the way through df by dxn. So this is the definition of the gradient of a scalar function with respect to a vector. We just take the partial derivative with respect to each element of x. And just to be clear, x here is equal to x1, x2, and so on, all the way through xn. All right, so let's go and do a quick example showing how we can take the gradient of a particular scalar function. So let's say we have the function f is equal to x transpose y, and we want to take the gradient of this scalar function with respect to x. So note that this is also equal to y transpose x. Why is that the case? So note that this is a scalar. This inner product produces a scalar, and the transpose of a scalar is equal to itself. Right? So we can always just reverse the order or take the transpose if we're dealing with an inner product like this. Unless it's in the complex domain, then we have to take the conjugate transpose. Right. So this expression here is equal to x1 y1 plus x2 y2, and so on, all the way through xn yn, right? So let's say we want to compute the gradient of our expression f with respect to x. So we look at our expression here. We have to compute df with respect to x1, df with respect to x2, and so on all the way to df with respect to dxn. So what is the gradient of f? What is the partial derivative of f with respect to x1? It's equal to y1, right? So all of these other terms will go to 0. This term, the x1, will go out with the derivative, and we end up with y1. Similarly, df by dx2 is equal to y2, right? So we can compute the gradient. The gradient will simply be equal to y1, y2, all the way through yn, which is equal to our original vector y. Okay, so the gradient of this inner product with respect to x will just return our original vector y. Okay, let me have you do a quick example here. Let's look at f is equal to x transpose x. Okay, and what I want you to do is I want you to tell me what is the gradient of f with respect to x. I'll give you about 30 seconds or about a minute to figure that out. And if you know the answer, I'll give you about 30 seconds and then you can just volunteer it, okay? Okay, does anyone have an answer for the gradient of this function with respect to x? 2x, exactly. So how did we get that? Well, x transpose x is equal to x1 squared plus x2 squared, and so on, all the way to xn squared. If we take the gradient or the partial derivative of this scalar function with respect to each of these, we end up with 2x1, 2x2, all the way through 2xn, which gives us 2 times our original vector x. Okay, so very good. So when you want to compute these gradients of a scalar function, it's easiest to just write them out and then compute the partial derivatives with respect to that scalar expression. Okay, so very good. I'm going to give you a couple more identities here. So we showed that these are going to be necessary later on in class. So I will give these to you. So these are some common ones. So dy transpose x by dx is equal to y. We have that, as you showed, dx transpose x with respect to dx is equal to 2x. And there's some other important ones that we're going to need. Let's say we have dy transpose ax, where A is a matrix, an n by n matrix. We're taking the gradient with respect to x. This will give us A transpose y. And you can find this just by applying the same process we did before. I won't go through it, but this is another identity that we're going to need. And finally, if we have the expression dx transpose ax, this is called a quadratic product. If we take the derivative of this with respect to x, or the gradient of this expression with respect to x, we get A plus A transpose times x. Okay. And if A is symmetric, you'll end up with 2A times x. Okay. And often you will end up with an expression that is symmetric inside of that quadratic product. So that's another common form to remember. All right. Great. Well, with that, we can move on So we're going to start talking about overdetermined and underdetermined problems. These occur all over the place in engineering, and you've probably encountered them before. In fact, you've almost certainly encountered the overdetermined problem. Let's talk about overdetermined and underdetermined problems. Okay, so we're going to be considering a linear transformation, A. And A maps us from our November, Rn, to Rm, our Mike. Okay, and we're going to be interested in equations of the form Ax is equal to y, where A is known, y is known, and x is unknown. X is what we're trying to figure out. So this is an extremely common type of problem. It's used very commonly in all sorts of numerical solvers for CFD applications or just general mechanics problems. You've almost certainly encountered an equation like this before. We're going to be using it specifically for the problems of controllability and observability later on, but it's a very, very general problem in engineering and data science, statistics, all of those domains. Okay, so there are three cases that are possible. And I'm going to go ahead and enumerate them for you. Okay, the first is the easy case. This is the nice case, where our matrix A is square. In other words, M is equal to N. And just to be clear here, X is in Rn and Y is in Rm, as in Mike. So the first case is the case where A is square. This is the nice case, because if A is invertible, or in other words, if it's full rank, then we can find our solution X explicitly. So we have the equation Ax is equal to Y, right? So how can we find a closed form expression for X? Right. So we pre-multiply by A inverse on both sides. So we'll get A inverse A times X is equal to A inverse Y, and therefore X is equal to A inverse Y. So easy peasy. Note that in practice, if you're solving equations with the form Ax equals Y, you generally don't want to do this. You don't want to explicitly take the inverse. It's usually more numerically efficient to use a numerical solution procedure like Gaussian elimination or other kind of factorization methods to solve this problem. But conceptually, what we're doing is we are pre-multiplying Y by A inverse. That will give us the explicit solution to this problem. Okay, are there any questions on case one? So this is probably one that you're familiar with. Note that this is only possible if A is full rank. So even if A is square, it has to be full rank to apply to determine an inverse. Otherwise, there is no inverse for A. All right, so the next case, case two, is the overdetermined problem. So this is where our A matrix is tall. In other words, M is greater than N, so the number of rows of A is greater than the number of columns. Okay, so let's draw this out. So we have some tall matrix A being multiplied by some shorter vector X is equal to a tall vector Y. Okay, so this is the overdetermined problem. Who's encountered a problem like this before? Some of you have. So what context have you encountered an overdetermined problem? First of all, what does it mean if our A matrix is tall? if the number of rows are greater than the number of columns. So X is our vector of unknown entries or unknown parameters. We're trying to solve for X. The number of rows is greater than the number of columns. So what does that mean? You may have heard this phrased this way in engineering before.
Like normally we need one equation for each variable, so now we have too many equations.
Right. So there are more equations than unknowns, right? You've probably heard it phrased this way before. Each row represents an equation, and the elements of X represent our unknowns. So in this case, there are more equations than unknowns. So what happens when there's more equations than unknowns? First of all, does a solution to this system of equations exist? Is there a unique solution to the system of equations? So I'll put a little question mark here. It turns out that no solution exists. No solution exists that can satisfy all of these equations simultaneously. So that is the nature of a overdetermined problem. There's more linearly independent equations than unknowns. And therefore, there is no vector X that can satisfy this system of equations and make Y equal to AX. Did you have a question, Jimmy?
Yeah, so but if A has a number of equations which are not linearly independent, such that you do have n number of linearly independent equations, even if our A matrix is all, is that still not a linear solution?
So if it turns out that if enough equations are collinear, so you can think, we'll do some examples later where we'll be looking at points on a plane. So it turns out if you have enough points that are collinear, you can formulate a set of parameters X that satisfy those equations. But if there are more equations than there are unknowns, it'll become more clear when we do an example later. But there's essentially, you'll end up with a situation where you have a cluster of points and no way to draw a line through them, essentially. And you'll see, it'll become more clear in a little bit. Okay. So for the overdetermined case, there is no solution that can satisfy all of these equations simultaneously. So what we want to do is find the vector X that gets us closest to the solution that we can possibly get. So in other words, the closest we can get is to minimize the error between AX and Y. Minimize the error between AX and Y. Okay, so there's no solution that exists for this overdetermined system of equations. So what we're going to do instead is we're going to try to find the next best thing. We're going to try to find the X that gets us closest to satisfying the system of equations. And we can do that by setting this up as an optimization problem. So if we're stating this is an optimization problem, we want to find X hat. So this is essentially our best approximation of X, the X that gets us closest to our desired system of equations. So we can set this up as an optimization problem. I'm going to say that X hat is equal to argmin AX minus Y. So this is here is the 2 norm of AX minus Y. Essentially what we want to do is we want to find the X that minimizes the difference between AX and Y. So we're minimizing the error between AX and Y. And note that if this is overdetermined, there will be no x that gets us to 0, right? Ax cannot equal y, but we're finding the x that gets us as close as possible to 0. Okay, so we're setting this up as an optimization problem. And we're going to use the identities that we formulated earlier to solve this. So there's a couple of things we can do first to make this a little bit easier to solve. The first thing is to note that the x that minimizes this norm, that minimizes the difference between ax and y, the 2 norm, is also the x that minimizes the square of that norm. And the next thing we can do to make this easier is the x that minimizes this norm here also minimizes 1/2 times this entire norm. Okay, and with that, we can go ahead and set up a cost function. So let's set up a cost function. We're going to say that h, our cost function, is equal to 1/2 times the norm of ax minus y squared. This is the 2 norm of ax minus y squared. We want to minimize the error between ax and y. Okay, note that the 2 norm of ax minus y squared is simply equal to the inner product of ax minus y with ax minus y. This is just from the definition of the 2 norm. It's equal to the inner product of ax minus y with itself. Okay, so how can we re-express this inner product? Well, the inner product of ax minus y with itself is equal to the transpose of ax minus y times ax minus y. So if we take the transpose of this expression, we get x transpose a transpose minus y transpose dotted with ax minus y. All right, and next, all we have to do is we have to carry out this multiplication. So we end up with x transpose a x. Let me just put the vector notation on all of these. Yep. Okay, minus x transpose a transpose y minus y transpose ax plus y transpose y. All right. Cool. So we've expanded out our cost function. Now, one thing to note, if you've taken Dr. Sella's class in optimization, what's one nice thing about this cost function that we've created? What's a nice property? Can anyone see it? We have our cost function is a quadratic product. And quadratic functions are what? What makes them nice for optimization? They're convex, right? So this is a convex. This is a convex problem, which means that we can efficiently find a solution. We can efficiently find a global solution by taking the derivative of this cost function and setting it equal to 0. Okay, so we can find a global solution by taking the derivative with respect to x and setting it equal to 0. And luckily, we wrote down those identities from before, which will make this a lot easier. So we're going to take our cost function h and set it equal, take the derivative and set it equal to 0. So we have that dh by dx is equal to 0. And if we go through each one of these terms here, this first one becomes we look at our identities from before, sorry, it becomes A transpose A plus A transpose A times X. Okay, we're treating this A transpose A as just a single matrix. So the derivative becomes this expression here, A transpose A plus A transpose A times X. This expression here, what does this become if we take the derivative with respect to X? It's from one of our identities that we wrote down earlier. What does this one become? So this one, it'll be A transpose Y, right? A transpose Y. And what about this one here? So first of all, what's the relationship between these two here? They're the same thing, right? So this will also be A transpose Y, right? These are both scalars. The transpose of a scalar is equal to itself, and therefore the derivatives of both of these with respect to X are A transpose Y. And finally, what's the derivative of this with respect to X? 0, exactly. Okay, so we can go ahead and write this out. We have 1/2 times A transpose A plus A transpose A times X minus A transpose Y minus A transpose Y. Okay, note that this here will just become 2 times A transpose A plus A transpose A. This will become 2A transpose Y. So the 1/2 goes in and takes care of those. And we end up with 0 is equal to A transpose A times X minus A transpose Y. All right. If we rearrange this, we get A transpose A times X is equal to A transpose Y. And then all we need to do to find X is, what can we do to find X? What can we do to find X from this expression here? We can pre-multiply by something, right? Yeah, so it'll be A transpose A inverse. If we pre-multiply on both sides by A transpose A inverse, we will get X hat, our optimal X is equal to A transpose A inverse times A transpose Y. So this is our expression for the X that minimizes the error between AX and Y. Okay, who's seen an expression like this before? Who's seen an equation? Who's seen this equation before? Anybody? So this is called the left pseudoinverse of A. If you've ever done a linear regression problem, you have used this equation, essentially, right? So it finds the vector X that minimizes the error between AX and Y. So this is kind of, it's a fundamental equation for solving overdetermined problems that occurs all over the place in domains like data science, where you often have more data than you have unknowns, or more data than unknown parameters, more equations than unknowns.
So A transpose A for any is invertible?
Not necessarily. So if it's not invertible, you'll have to use what's called the Moore-Penrose pseudoinverse, and that you can obtain using a technique called singular value decomposition, which originally I was planning to get through, but we're not going to have time this semester to get through. But yes, it is possible to come up with a generalized pseudo-inverse that works even if A transpose A isn't full rank. And as we saw before, it's possible for that to occur if there are basically zero or linearly independent, linearly dependent rows or columns in our tall A matrix. Yeah. Okay, so another term you might hear, this is also called the least squares solution. So if you hear the term least squares, it usually refers to solutions of this form, the least squares solution to an overdetermined system. Right, are there any questions on this derivation or these concepts? Cool. So I would actually go ahead and recommend memorizing this equation because it pops up all over the place. And especially overdetermined problems occur very frequently, especially if you're doing anything with machine learning or data science where you have a lot of data and you're trying to fit a model to it. So I would actually recommend memorizing this equation. All right. So case 3. We talked about case 1 where there's the number of equations is equal to the number of unknowns. We talked about case 2 where there are more equations than unknowns. Case 3 occurs when there are more unknowns than equations or where A is wide. Okay, so the number of columns of A is greater than the number of rows. Okay, we can write this out. So we have A, it's being multiplied by some taller vector X. And it's producing a shorter vector Y. And we're trying to find this vector X for this system of equations. Okay, so we have more unknowns than equations. Is there a solution to this system of equations? Is there a solution? There is a solution. Is the solution unique? No. So there are infinitely many solutions. There are infinitely many X vectors that can satisfy the system of equations. There are infinitely many vectors X that satisfy the system of equations. So what can we do? Well, we're interested in finding the best solution to this equation, AX is equal to Y. There's infinitely many solutions. One interpretation of the best solution is to find the X that has minimum norm. Okay, so one interpretation of the best solution is the X with minimum norm. And you'll often find this if you're working on, for instance, problems where you have, you're trying to, fit a curve or something. And there are multiple different curves that can go through those points. We want to find the parameterization that's minimum norm to prevent essentially overfitting or to prevent. So for instance, if you have a curve going through all these points, you don't want the curve jumping up and down all over the place, right? So in general, you want the curve that has the minimum norm. And one way to do that is to solve the following constrained optimization problem. Okay, so there is kind of a best solution. I'm going to go ahead and formulate it as an optimization problem, just like we did before. Okay, so what we're going to do is we're going to find our optimal solution X where we want x to satisfy the equation ax is equal to y. And we want to find the x that minimizes the norm of x. So we want to find the minimum norm x that satisfies this system of equations ax equals y. So just as before, the x that minimizes this optimization problem also minimizes the square of this optimization problem. And we can also go ahead and pre-multiply by 1/2 as well. Okay, and note that we can also rewrite this using the definition of the norm. This is equal to argmin x, argmin over x of 1/2 x transpose x. Okay, so we have a constrained optimization problem. For those who have taken Dr. Stella's class, what's one way that we can solve a constrained optimization problem like this? What's kind of a general solution procedure for finding solutions to constrained optimization problems like this one? I think I heard it. Sorry? So one thing we can do is we can take this constrained optimization problem and convert it into an unconstrained optimization problem, right? What's that technique called? Does anyone remember? So this is an important one. Does anyone remember the technique of Lagrange multipliers? Right, Lagrange multipliers. Okay, so what we're going to do is we're going to take this constraint and we're going to put it back into our objective function as a penalty term. So we can rewrite as an unconstrained problem. Okay, and we're going to say that we want to define a new cost function here. So we have that h is our cost function. Okay, and we're going to take our original cost function, 1/2 x transpose x. And we're going to add a penalty term, which will be equal to lambda transpose. So this is our Lagrange multiplier, our vector of Lagrange multipliers lambda, multiplied by ax minus y. Okay, so we're penalizing deviations from ax is equal to y, essentially. We want to minimize both of these terms. And from the method of Lagrange multipliers, we know that the optimal solution to this problem is found when dh by dx is equal to 0 and dh by d lambda is equal to 0. So let's go ahead and try that. So if we compute dh by dx, we have this we know is just going to be x, right? Plus this expression here will eventually, if we take the derivative with respect to x, we will get a transpose lambda. And the other term with the y just goes away. Okay, and this is equal to 0. Next, if we take the derivative of our cost function with respect to lambda, what we will get is, well, we'll just get this expression here, right? Ax minus y is equal to 0. All right, so let's go ahead and manipulate this a little bit. So note that also when we apply this method of Lagrange multipliers and take the derivative with respect to lambda, what does it do? it recovers our constraint, right? So at the optimal value, our constraint is satisfied. AX is equal to Y. Okay, so let's go ahead and manipulate this a little bit. We're taking our first expression here. We know that if we just rearrange this, we get that X is equal to negative A transpose lambda. Okay, let's go ahead and pre-multiply by A. We have that AX is equal to negative A transpose lambda. Okay, and we can find lambda by pre-multiplying by the inverse of AA transpose. So we have that lambda is equal to negative AA transpose inverse times AX. And we know that AX is equal to Y. So we have that lambda is equal to negative A transpose inverse times Y. Okay, if we take this and we substitute it back into the first equation, we have that X is equal to negative A transpose lambda, and therefore X is equal to, if we substitute in this expression for lambda, we get negative A transpose, negative A transpose inverse times Y. Okay, and if we take these negatives and let them cancel out, we end up with X hat, our optimal X is equal to A transpose times A transpose inverse times Y. Okay, so note that this kind of looks a little bit like the other one, right? This here is called the right pseudoinverse. And again, what this does is for an underdetermined problem where there's infinitely many vectors X that satisfy our system of equations, it finds the solution X that is minimum norm. Okay, and towards the end of class, I'm going to show you how this relates back to the 4 fundamental subspaces that we talked about last week. So this problem, I would say, is less common in general than the overdetermined problem. It's one that you see usually less often, but in controls, it comes up in terms of the problem of finding a control input that drives the system from some initial state to some desired final state. There's often more than one control input that will do that, and often we want to find the control input that is minimum norm. Similarly, the overdetermined problem we'll see comes up in the problem of estimation, where we have a time history of measurements of the system, and we're trying to recover the state of the system at some previous point in time. It turns out that that relates to the overdetermined problem. And I'll show you some examples towards the end of class if I have time. Okay, are there any questions on undetermined and overdetermined problems, the theory, before I move on? I'm going to do some examples to make this a bit more clear. Okay. Cool. Who's seen any of this stuff before, by the way? Just checking. Has anyone seen this in like a machine learning class or a optimization class? Okay. Cool. Well, now you know how those solvers come up with the equations to solve for linear regression. This is basically how it's done underneath the hood. Okay, and with that in mind, let's go ahead and do an example of a linear regression problem. We're going to do linear regression by hand. Turns out to not be as difficult as you might think. Let's first take a look at an overdetermined problem. And this is going to relate to the problem I was talking about with Jimmy earlier in class today. Let's say we have just some set of points in R2. Okay, we have just a set of points in a plane. So this will be our x-axis. This will be our y-axis. A few tick marks here. Got some tick marks. Okay, and let's create a cluster of points in this plane. Let's say we have a point at -1, -1. Let's say we have a point at -1, 1. Let's say we have a point at 2, 1. And finally, let's say we have a point at 1, 0. Okay, and this is going to be a kind of a classical linear regression problem. What we're going to do is we're going to try to find the equation for the line of best fit through these points. Okay, so our objective, that's not how you spell goal. Goal is to find the line of best fit through these points. Okay, so we know that our equation is going to be of the form y is equal to mx plus b. And the classical equation that you learned in middle school. Okay, and we have, how many equations do we have here? How many equations do we need to satisfy? 4, right? So let's go ahead and draw those equations out. So we have that y1, y2, y3, y4 is equal to m times x1, x2, x3, x4 plus b times 1, 1, 1, 1. Okay, so we can take this equation here, and we can rewrite this as a matrix vector product, right? So we can rewrite this as y1, y2, y3, y4 is equal to some matrix where the first column is x1, x2, x3, x4. Second column is 1, 1, 1, 1. And it's being multiplied by a parameter vector, MB. So note that this is equivalent to this equation here. We've just wrote it as a matrix vector product. Okay, so what we can do now is, how can we solve this problem? First, what do we need to do to get some numbers in here? So we know that each of these x1s represents the x coordinate of each of these points, right? So let's go ahead and fill those in. Let's fill in the coordinates for y as well. Okay, so just starting from this point here, we have that x is -1, y is -1. We have that x is -1, y is 1. We have that x is 1, y is 0. And we have that x is 2, y is 1. So we have this matrix equation now, where we have that y is equal to some matrix A times what I'll just call theta, which is our parameter vector containing m and b. And we're trying to solve for theta, right? We're trying to find the m and b that satisfies the system of equations. Is it possible to satisfy the system of equations? Is there a line that will go through all of these points? No, right? There is no solution to this problem. So what can we do to find the best set of parameters m and b for this problem? Least squares. So which pseudo inverse do we use? Left. So the answer is given by the left pseudo inverse. Okay, we have that our optimal theta, our optimal vector of parameters m and b, is equal to A transpose A inverse times A transpose Y. Okay, and so we can go ahead and write this out. I'm just going to write it out once here. We have that A transpose is equal to -1, -1, 1, 2. Second row is all ones. Okay, multiplied by A is just going to be the same thing, transpose, so -1, -1, 1, 2, 1, 1, 1, 1. Take these two, multiply them together, and take the inverse. And then we got A transpose again, so that's -1, -1, 1, 2, 1, 1, 1, 1, all multiplied by Y, which is -1, 1, 0, 1. And you can go ahead and you can calculate this by hand if you wanted to. I actually had to do this on a test when I took linear systems theory in grad school. So you can compute this by hand, and what you'll end up with is the vector theta hat is equal to 7 divided by 27 and 5 divided by 27. So you'll end up with your slope, your optimal slope m being about 0.26, and your optimal offset b being equal to 0.19. Okay, so that's all that's happening when you're doing linear regression on a computer. It's essentially solving this system of what are called the normal equations, or the pseudo inverses. And as I noted, there is no line that will go through all of these. You'll end up with something like this. And it's called least squares because it's minimizing the squared distance between each point in that line. Okay. Are there any questions on this example before I move on? Cool. So let's do the other one. Let's look at the underdetermined problem. Okay, so as before, we have our R2 plane. And this time we're only going to have 2 points. So let me draw a set of ticks here. Okay, so we got a point, let's say we have a point at -2, -1. And we have a point at 1, 1. And let's say we want to find, I can't spell goal for some reason, goal. We want to find the equation of a cubic polynomial that goes through these points. Okay, so our cubic polynomial will be of the form y is equal to a3 times x cubed plus a2 x squared plus a1x plus a naught. And we want to find a cubic polynomial that goes through these points. So first of all, as you can see, there's an infinite number of cubic polynomials that'll go through these points, right? You may have one that goes like this. You may have one that goes like this. Right? There's many, many different cubic polynomials that'll go through these points. What we want to do is we want to find the one with minimum norm. In other words, the ones where the parameters a0 through a3 are of minimum value, right? In the squared sense, or in the 2 norm sense. Okay, so just as before, we can set this up as a matrix equation. Okay, we're going to write this out as before. we have our parameter vector. This time our parameter vector will be A3, A2, A1, A0. And our Y vector will be over here on the right. It's actually going to only be 2 elements tall. So we'll have Y1, Y2. Yes, Y1, Y2. Okay, and what are the elements inside here going to be? So first of all, there's going to be 4 columns, right? There's 2 equations here. So each of these columns here will be over on the far right side, we'll have 1, 1 corresponding to the ones place. The next column over will have x1, x2. The next column over will have x1 squared, x2 squared, and the next column over will have x1 cubed, x2 cubed. Okay, so let's go ahead and fill these in. All right, so our y1 and y2 will be, let's go with this point on the left here first. We will have -1 and 1 for our y vector. For the row of x terms, we'll have -2, 1. Okay, what will be this column here? Sorry? So this term here will be x1 squared, right? So it'll be 4. And this term here will just be 1 because 1 squared is 1. Okay, and what will this term here be? -8. Very good. And this term here will just be 1. Okay, so just as before, we have a times theta is equal to y. And we're trying to find the parameter vector theta that satisfies the system of equations and is also a minimum norm. So how can we do that in this case? What equation do we use? We use the right pseudo-inverse. Okay, so the right pseudo-inverse gives the minimum norm theta that satisfies our system of equations. So that will be theta hat is equal to A transpose times A transpose inverse times Y. I'll go ahead and write it out for you. So we will have here -8, 1, 4, 1, -2, 1, 1, 1 times this quantity A transpose. So that'll be -8 for -2, 1, 1, 1, 1, 1 times its transpose, -8 for -2, 1, 1, 1, 1, 1, all inverse times -1, 1. And if we do that and compute the value for our parameter vector theta hat, what we end up with is the following values for our parameters A3 through A0. So A3 hat will be equal to about 0.23. A2 hat will be equal to about 0.27. A1 hat will be equal to about 0.25, and A0 hat will be equal to 0.26. So note that they're all kind of close to each other. And that'll kind of occur when you use the 2 norm as your minimizing norm, that they'll tend to kind of be a similar magnitude. Okay, great. Are there any questions on the underdetermined problem before I move on? So it's essentially to prevent, like if you go back here, you have multiple different, so in the context of control, it makes sense because you're finding the minimum norm control input. So in other words, there's many ways that you can drive the system to some final state that you want, but in general, you want the one that minimizes the control energy put in. In this case, it would kind of correspond to, you might have like a cubic polynomial that's like this, or it may go all the way up to infinity or something, right? But in general, you want the one that's kind of the minimum effort. Something that goes like that. Okay, good question. All right, so let's quickly recap how this relates to the 4 fundamental subspaces. I don't have too much time here, but let's go ahead and just relate this back to how it corresponds to what we were talking about before. First, let's talk about the overdetermined problem and how it relates to the 4 fundamental subspaces. So I'm going to draw our fundamental subspaces out like this. Okay, we have our little diamonds. Right. So for the overdetermined problem, let me just finish labeling these. We have RA transpose, null space of A, the range of A, and the null space of A transpose. For the overdetermined problem, we said that there's no solution to our overdetermined system. And what that implies is that Y, our vector in the codomain, is not in the range of A. If we go back to our set of points here, there's no way that we can define a parameter vector M and B such that A times that vector gets us Y. There's no way to combine the columns of A together to produce Y. So for the overdetermined problem, Y is not in the range of A. So it kind of exists out here somewhere else. In particular, it's a combination of a component from the range of A and a component from the null space of A transpose. Okay, and I'll call this vector here in the null space of A transpose, I'll call this Z. And this vector here in the range of A, I'll call Y hat. Okay, so what we're doing when we're solving the problem for the left pseudo inverse is we're finding a point X somewhere in our domain that maps to Y hat. Y hat is the orthogonal projection of Y onto the range of A. So in other words, Y hat is the point that is closest to Y, our desired solution, that lies within the range of A. So if we find the projection of Y onto the range of A, that gives us Y hat, which is essentially the closest we can get to our desired solution. Okay, and this vector here would be X hat. So it is X hat we saw from the left pseudo inverse is equal to A transpose A inverse A transpose Y. Right, so taking this a little bit further, we know that our optimal X is equal to A transpose A inverse times A transpose Y. We know that Y hat is equal to A times X hat. And thus Y hat is equal to A times A transpose A inverse A transpose Y. So this here is the projection matrix onto the range of A. So in other words, when you take this matrix here and you apply it to Y, it finds the projection of Y onto the range of A and will give you y hat. So in other words, it's the closest point in the codomain to y that lies within the range of A. All right, let's quickly talk about the underdetermined problem. Yikes. I'll try to make it out in time here. Okay, so just as before, we have our fundamental subspaces. Forgive me if I go a minute over here. Okay, so we have the range of A transpose, we have the null space of A, we have the null space of A transpose, and we have the range of A. All right. So for the underdetermined problem, we have some desired point in the range of A that we're trying to reach. Okay, so we'll call this Y. And this time we can reach it. But there are multiple points in the domain that map to our desired solution Y. So let's draw those lines here. So all of these different vectors in our domain map to our vector Y in the range of A when you apply A to them. And each of these vectors in our domain that map to Y consist of some component from the range of A along with some component from the null space of A. So each one of these, there's this component from the range of A, from the range of A transpose. And there's also a component from the null space of A. So we can write this out. Let's call each one of these. So let's call this point here, let's call it X hat. These points here, I'll call just V1, V2, V3. All of these map to Y in the codomain. So we have that for each of these vectors that map to our desired point Y, they're equal to some component from the range of A transpose plus some component from the null space of A. So let me write that this is from the range of A transpose, and this is from the null space of A, and I'm almost done here. So what happens when we take these points? So these correspond to these 3 points here, V1, V2, and V3. What happens when we apply A to these points? We'll get that Y is equal to AVR plus AVN. Okay, what happens to this point here when we apply A to Vn? It goes to 0, right? So that's why there are multiple points in the domain that map to our desired point in the codomain, because that component from the null space, when you apply A to it, it just goes to 0. What this also means is that this component from the null space, of A is wasted. So it contributes to the norm of our vector in the domain, but it doesn't change where our vector lands when we apply A to it. So what we're doing when we are finding the solution to the underdetermined problem is we're finding the projection of these points onto the range of A transpose. By removing that component from the null space, you are ensuring that you have the minimum norm vector that maps to your desired point in the codomain. All right, I'm out of time, so I'm going to go ahead and let you go. Just remember that there are office hours today at 4. Feel free to talk to me about the homework, and homework 5 is postponed until Thursday. You heard it first here. So great. Go ahead and have a great day, and I hope to see you at office hours this week.